Okay, now I have to be professional. So let's review polar spherical coordinates, which is, you know, the chapter doesn't matter. So the first thing I will do, polar spherical. This actually will be a good problem. Just you should not be scared of seeing a lot of square roots, because it's the whole point. We introduced to you spherical and cylindrical coordinates exactly for that reason, not to deal with square roots and other stuff. If something is rotational, especially around everything, then use spherical coordinates. If something is rotational but fixed in height or width, that's cylindrical. But for example, either they ask you to build it, you might have both examples actually. Squared dx, dy, dz. And then they will say over E, and then E is the ball, radius 2. And then they also say first octant. You need to remember the formula. So first of all, lots of formulas actually, but rho, let me do all of them, I guess. But definitely x squared plus y squared plus z squared is rho squared. That is good, and it's known. Then x is rho. I remember it like this. It was hard to memorize these guys, so I will give you the hint how I memorized that. Rho cosine theta, rho sine theta. That is what we have from the polar part. And then spherical, since it's in 3D, takes polar into third dimension as well. Adds sine phi to both. And then since we never used cosine phi, it goes to the last part. That's how I memorized. Maybe it's helpful, I don't know. I always try to find some trick to memorize formulas. And the idea was of this, the whole sphere will be, any point on the sphere can be represented with 3 points, rho, phi, and theta. Rho will be the radius, but now it's radius in 3D. How far my point is away from the center. Theta, which is, comes second actually, I think. That doesn't matter. I want you just to explain how it works. Theta gives the full rotation in 2D. Yeah, actually everything is correct. This is in 2D. A rho is happening in 3D. But theta is rotation in 2D, flat. That part is coming from polar, and that's why it is from 0. Theta. Theta is a circle with the wiggly part inside. To 2 pi. However, phi is only from 0 to 1 pi, because it creates the angle from north pole to south pole, like so. Yeah, up. So how away I am, that's my theta. And then like so, I should change colors, is phi. Phi is not creating the full circle, because that will be overkill, since theta already did the whole circle. That is the idea. Yeah, that's how usually we explain it. You don't have to have both from 0 to 2 pi, and that's why we decided that phi will be doing only up or down, but not the whole thing. Kind of intuitionally, that's how you should see it. So yeah, that's how I would explain it. Then from all this stuff happens in the formula, which is integral. That is going to be rho squared, but it was already squared. So we don't forget to square that. And then the trick is that there's also a formula involved. Scroll back. Keep losing my files. Hopefully you remember the formula. Remember, there's always a tail of the integral, which you should not forget. Used to be the pirate story, and it still is. It's still R, dr, but it's a little bit more than that now. So found it. How come I keep losing the PDF file? So in this case, it will be rho d rho, kind of like in the pirate, but it's somehow rho squared. Anyway, it comes from the derivation. So if you want to see the proof, you just do that. Usually students ask, how did this all happen? And we say, well, if you really want to, go check the proof. But the tail is rho d rho, but rho square, sine phi d rho d phi d theta. I always show this formula in calculus 1 and 2 to freak people out. And this is what they will see in calculus 3. The way to see it, we have two angles now, phi and theta, and each has a radius. So that's why there are two of them, kind of. And then sine phi represents that third dimension. So that third dimension that we're adding has a triangle, right triangle. So that angle also adds up. Kind of, that's how vaguely we can explain it if you don't want to see the proof. Yeah. So I would show, oh, I see good notes. Full north and south poles. Like so. But if we have only one of them, then it will be from 0 to pi over 2. That is just n, for example, just north or just south, like so. That's a good example. And finally, we can complete it. Rho goes first in this formula, as you can see. Rho is given ball radius 2 from 0 to 2. If it's between two balls, get what you do. Inscribed in a bigger ball, but outside of the smaller ball. You had it in your homework and you might have it in the test, so definitely review these. Then it will be from whatever this radius is, 5 to whatever this radius is, 11. Then it's going to be integral from 5 to 11. Those kind of things, definitely review them. But I think these are actually intuitionally nice problems. Intuitively easy to catch them. And then first octant means something. Radius is still fine, but first octant restricts the angle. So if you remember, first octant is where all three are positive. Let me make a note. First octant is phi should be positive. First, not just positive. Oh. The whole circle is fine. Oh yeah, positive, but phi doesn't go both north and south. Yeah, that's the idea. Positive we usually say for x, y, and z. That's why I was thinking for a second. First octant is x is positive, y is positive, and z is positive. From here, kind of you can check out the trigonometrics, which angles make some of these negative. So at pi over 2, 0, pi over 2, pi. At pi, cosine is negative. Yeah, and that's why we don't go to pi anymore. Cosine will be negative here, I think. So that's why z, which goes down, should not go down. Not to go down for z, we need to restrict phi to be from 0 to pi over 2. From 0 to pi over 2, that's phi. From 0 to pi over 2. And then theta, remember, is into d. Into d. Is it the full circle or not? See, now I'm getting confused as well. What do you think about theta? Will it go to the from 0 to 2 pi or not? First quadrant.
The first quadrant is just going to be from 0 to pi over 2.
That's for phi, but for theta.
No, for theta too, because you're going
theta.
from the first octant, so that's only going to be from the x-axis to the y-axis.
Mm-hmm.
So it's going to be from 0 to pi over 2.
Yeah, I think you're right. 0 to pi, also to keep x, y, and z positive. Yeah, first quadrant. From 0 to pi over 2. So I remember at some point I just memorized these cases. The first quadrant is you're doing this, and then others, it's usually the first quadrant, so it's fine. Sometimes it's the upper half and lower half, and that is when theta will be from 0 to pi over 2. Oh, that's actually exactly what I wanted to mention. First quadrant, phi cut off from 0 to pi over 2, and theta, yeah, thank you for your help, from 0 to pi over 2. But for the upper half, then you have x positive, x and y are any, x comma y, any, but z is positive, and to keep z is positive, that will be a theta is spinning around like crazy, but phi cannot go down to the south pole. So it is from 0 to pi over 2, like so. Okay, good. I got it. Good. Those are polars. There was some kind of problem I wanted to show. I wanted to make a list for you. What to review? Review. 2 spheres. Let me make it clear. Between 2 spheres. Then there was a lines and first quadrant in a circle, those kind of things, bounded by lines and the circle, and there's also the first quadrant. Those things, I saw them in your homework, so review all those restrictions. And then just stuff. It's funny, but I will show you what I mean. Just stuff. Don't be afraid if they just give you stuff with no explanation. Then just figure it out. Example for just stuff. I actually have it here. Integral from -2 to 2. Integral from minus a square root. So when you see lots of square roots, that's when they expect you to figure out polar coordinates. Integral from 0 to square root 4 minus x squared minus, what is that? What kind of horrible writing is that? It's my writing. Xy squared, yes. E to the x squared plus y squared plus z squared d z dy dx. And they say convert this to polar coordinates. You see, actually now I understand why I got stuck with the first octant. I got confused with the first quadrant. First quadrant and first octant, not the same thing. So if we have, they also say in this case, first quadrant. So pay attention to that. Quadrant is in 2D. And it looks like this. That means x and y should be positive, but z is any. So that's why it's not the same thing. Okay, when you convert all of these, you follow some either common sense or you make a picture. Usually we recommend to have a picture. Picture recreates everything really well. So it will be integral e to the rho squared. Agree? Because the whole thing here is rho squared. Then I write my formula right away. I would recommend that when you start your test, have a blank piece of paper and write down all the formulas you remember. That's actually not cheating. If you take it from your mind, that's how I used to do. The exam starts, now you have to write everything you want. Write down the formula right away while you remember it. Rho squared sine phi d rho d phi d theta. Nice. So that's really good. That's your tail. Now radius is from what to what? Let's figure out that. Z shows up first. Z is from 0 to square root. Let's write it down. Z is from 0 to the square root. 4 minus x squared minus y squared. If you square these, that creates a circle. Well, a sphere actually. A sphere. Let me write it down nicely. Z squared equals, well, let's do plus x squared plus y squared equals 4. That's a sphere with a radius 2, right? Now you know. It's just not the whole sphere because of the square root. Z has to be positive. So now you know it's restricted. So rho showed up. And now you know that your rho is from 0 to 2. It also will come from other circles, so not only this one, but this is the way. This is 3D. For you to know, the first integral gives you a 3D picture. When you're done with the first inside integral, now you go into dx dy, but that is 2D. So that's why. Y goes next. Y is from minus square root to plus square root. That's the full circle in 2D. Y is between minus square root and plus square root. That's the stupid way to say that y covers the whole circle. So y squared plus x squared equals 4. So you see radius is 2 anyways, from 2D and from 3D. But we also have x. X, let's do different color, is from minus 2 to 2. What does that mean? X is from minus 2 to 2. That also represents the radius. The radius goes from minus 2 to 2. Anyway, what we need to know is that if we need to decide if it completes the full rotation or not. In 2D, it does complete the full rotation because of this information. If y goes from minus square root to plus square root, that's a full circle. Full circle. Since it's a full circle in 2D, then theta is responsible for full circle in 2D. So theta will be from 0 to 2 pi. Maybe the phrase about the first quadrant was about a different problem. Oh, no, it's fine. But phi is not going down to the negative z. This kind of restricts phi. Phi cannot be, phi has to be positive because it's upper half of the sphere, z. It looks like so. The sphere, and we only use upper half like so. The full circle goes around. That's my theta. Radius is 2, but we never go to the south pole. Because of that, phi is between 0 to pi over 2. From 0 to pi over 2. Yeah, that is the idea. No problem, I just muted David. I know how to mute people. So, what do you think about that? Let me, not coffee. Yeah, that's, you can, Travis is like, that is a very good feedback. Let me have one more problem. I actually have also one more problem. Where did this come from? I think two. Answer number one. Top was pi. The top was pi. There's a question that's for phi. So it's not the top. You have to see it. You have to see the full rotation from the definition. The full rotation from phi is from 0 to pi over 2. If phi is restricted and phi goes from north to south pole, which is better to see from minus pi over 2 to pi over 2. But somehow people decide not to use that notation. So they decide to tilt the head and do from 0 to pi instead. Because it's more like the angle with this upper half. So if it's the whole angle, then it goes to pi. But if it's cut it off, then it's only half of the pi, and that's pi over 2. That's somehow the way I used to explain it. Maybe it makes sense. The whole thing, I'll just remember, the whole circle is from 0 to pi, then half of it from 0 to pi over 2, because it's tilted the angle up and down to north and south pole, kind of. Yes. So kind of, yeah. Because the original have 0 and the pi over 2 pi. No, definitely not from pi over 2 pi. That's the confusing part. Okay, let me show you the nice picture then, which we have here. Let's do it. That's a spherical coordinates. And then maybe the animation actually will help you also. Oh, there was nice coloring. I think coloring helps the best. Oh, look at it. So, wow, that is impressive. The thing around. Okay, that makes me feel dizzy. Let's do this. That was a little bit too intense. That is too pretty. Now let's go back to this one. I like this colored one. This one. Phi is this angle, like so. The farther, I would say it's 0 from here, from the North Pole. The farther away it is down, the bigger the angle. When it goes completely down, that is pi. When it passes only halfway through, that is pi over 2. Does that make sense? So this angle to the north, it's basically we're asking the question how far my point is from the North Pole. That is the angle phi. The thing around, the angle around is theta. The distance away from the pole is radius rho. Let's see it again here. Like so, and around. Yeah, I think this coloring one is the best one. Let me steal it. And then this one, that's not interesting. Like so. Nice. Let me write down. Yeah. So if it is the whole rotation from north pole to south pole, then it's going to be from 0 to pi. If it does the half, then to pi over 2. Yeah. This is kind of the idea. That's the most confusing part, always actually. Where this example came from? I wanted to show this one. It's somewhere in my notes. Let's see. Spherical formulas plugging in. Just don't mess up the phi, which is the hardest part. No, I think actually not too bad. That's what you need to, yeah, that's good enough for the spherical. Yeah. What is this? Spherical. X squared plus y squared. Oh, that's the one I already did. From 0 to pi over 2, from 0 to pi over 2. This one. And then you solve it. I actually never solved it. So hopefully you know how to solve those things. And I realized maybe I should show how to solve. Integral, integral, integral. That's the topic of triple integrals, how to even do them. So the best part is you can break them into 3 integrals in this case, because there's no functions involved in the limits of integrations. So if all the limits of integrations are numbers, constants, then you can break this integral, which is the last one, is working with theta. So let's find all the thetas in the formula. There's no thetas. So it's just 1 d theta. Do you know what this integral is? It's pi over 2, because if it is integral of 1, it always equals of the length of the interval of integration. And the interval of integration is b minus a, in this case pi over 2 minus 0. So that's the first one you can do. This is the first calculations. Second integral is responsible for phi. So it's from 0 to pi over 2. d phi, let's find all the functions of phi. Oh, it's sine only. That's nice. We know how to integrate sine. And then last integral is from 0 to 2, responsible for rho. Let's find all the functions of rho. It's rho 4 plus 2, 6d rho. See? So on the exam, when you're doing it like this, say out loud, it's not that scary if you break into 3 integrals, and that will make you confident. So pi over 2 is the first number. Second number, integral of sine is minus cosine, plug pi over 2 and 0. Maybe even keep it as it is. If you don't know, if you're afraid to make a mistake, it must accept your answer. But kind of hopefully you remember what is cosine of pi over 2. And then plus, because minus minus cosine of 0, which is 1. And then rho to the 7 over 7. So that's times 2 to the 7 over 7. And that is the answer. In my notes, the answer is 64 over 7 pi. Or 64 over 7 pi. Sure. Yeah, so that's good. No, that's good. Keep going. Next topic are fields. How do you feel about vector fields and all those beautiful but also confusing graphs? Vector fields. So someone posted in the chat vector fields about vector calculus. This is vector calculus. It just keep going later in more material, mixing up with differential equations. But this is vector calculus. We usually call calculus 3 vector calculus because of vector fields. So let me explain you some stuff. For example, contour map. How do you match contour maps? Contour maps and vector fields. I remember perpendicularity or the gradient and perpendicularity ideas. If you have a map, which is very realistic kind of map of the mountain. So this is a very steep mountain. Do you know how I know? Because you first need to climb a lot. Since you see those circles represents that it changes a lot. While here there's no change, right? So, and then here there is no change. So it means you first hike a lot and then it becomes not that steep anymore. If that is a mountain, maybe it's a pit, then it's the other way around. It's first not so much hiking and it becomes really hard to get up. So gradient shows you the fastest way to go down or up. That's why you call it gradient descent and gradient ascent. If you drop the ball, it should show you where to go fastest. It's perpendicular to those control maps. So you're supposed to see pictures like these. Moreover, if size matters, then the vector first is big and then becomes smaller and smaller and smaller because control maps also get smaller and smaller and smaller and smaller. That means, how to explain it? It jumps down faster. I guess that's how you can explain it. Yeah. If that's going up, in this case, going down the mountain, because I did it from inside to outside. This is the idea. And I will show you the end if I find fast in the email some super cool applications of control maps and stuff. Then I also wanted to show, how about these guys? I showed you last time this, super beautiful, like so. This looks like ocean maps and water currents, also very realistic ideas. Same thing, how would you match? We don't know actually it's going in and out, there's no information, we just have graphs. But one of the examples is, should be perpendicular. So either going to the right or going to the left, so we don't know. But at least you should see they should be perpendicular. See, this is the fastest way to get out or to get in. Maybe it even goes like so, or maybe to the left, we don't know. But the whole point should be perpendicular because that's the fastest way to move. Same thing like so, either up and down or down. So differential equations will teach you actually how to recognize different cases. Are they both going out? Or they go one direction, for example, or maybe they even swirl and create whirlpools and stuff like that. Finally, let's kind of all to the center, maybe out of the center, maybe like so. That's how you can match. Try to seek for perpendicularity. So these types of graphs, review that. Review matching. Fields with contour maps. Then remember you had homework with repulsive and attractive fields. Review that. I don't know, are you good at that or not? With repulsive and attractive ones. What do you think? Post in the chat. Do you remember repulsive and attractive one? Repulsive, that's the one that push away, and attractive, it pushes to. You good at this or not? Yeah, I can find the example later. So I want to show something with equations. Well, see, if you don't remember, this means you're not good, I guess. I should find it somewhere in the homework. But that's the question. And then I'm just deciding to keep it or not to keep it. Because, again, I kind of believe there are way too many graphs in the exam. Which is important. I understand why he wants it, because third exam has lots of vectors, fields, theory. So it's impossible for you to understand how graphs are correlated with control maps. But way too much matching. I'm not the one who actually, I'm the one who bad at matching things. It takes me forever. So I'm just afraid, is 2 hours even enough for so many graph matching? So that's what I'm asking. Are you good at repulsive? Someone should go and find time to find it. Which homework was it? Then we can review. Multiple choice might actually be good. That one was multiple choice. Yes. Keep it. Okay, then you guys review by yourself. Find the homework with these words. And again, lots of graphs. And review these. So I'll keep it. How about equations? Do you remember what this means? Minus yi and say plus xj. What does this mean? What kind of vector field is that? So this is very interesting. I kind of find it interesting, but again, do you understand the behavior? So for example, remember that component I responsible for moving to the left and to the right. right? So it's running. This is my I. It's at the same time X, but let's first concentrate on I. The more this coefficient, the bigger this let's start with J. It's actually easy with J. Component J, on the other hand, is responsible for going up and down. Let's start with J. The more the bigger and positive number in front of this J component, the more we are going up. The more it is negative, the more we're going down. So let's see how come it's reversed. X is the number on the left and on the right, not up and down. So the bigger my X, for example, 50, right? The more J will point up, not just exactly up. So it will be pointing, no, yeah, it will be pointing like so. Then next one will be higher and higher and higher, like so, kind of the idea. So that's the way you can see it. The more component in front of I, the higher, no, the bigger that component, the more we are going to the right. And in this case, it's hard to flip the direction. When I'm going very low, because negative y goes down, I'm going very to the right. So that's like so. So we already got this part. Now let's change the sign. The more I'm going to the left when x is negative, then the more I'm pointing down, 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 down. If x is 0, then I don't point up or down at all. Then I only point left or right. That is like so. When y is negative, so we're going, let's see, the higher your y. When y is negative, negative gives you positive, then I now points to the, anyway, I think you got the pattern already. And I think it looks like a whirlpool, like so. To the left while we're going to the right. This is what I want to explain. At the very end, I think explains more. The more I go to the right, the more it points up. The more I go to the left, the more it points down. At 0, it doesn't point up and down, so it's perpendicular. And completely the opposite way with I component. The more I go up, y is big number, negative sign makes it negative number. So I have to point to the left. The more I go down, y points to the right. When y is 0, it points exactly up or down. So it's a whirlpool. Oh. No, I don't think it's, do you think it's memorization? I guess if you have good memory, you can memorize. I actually like to think about it. And then unless you have like a brain glitch, when you just cannot do it anymore, then you kind of glitch. But if I concentrate well, I can feel like I can do it. Let's talk about the classic one, when both are positive and they correspond to corresponding I and J. So you don't, you don't like this? Well, I don't know, just let me know if you really hate this. This one's actually the one I like, to be honest. But there's also multiple choice. So this one is very classical one. It's either going out or going in. So check this out. The larger your y, the larger your j. So the more I'm going up, 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 the more I'm going up, 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 down, 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 down. Moreover, it also increases the magnitude. So the more I'm going away, the stronger it gets. And then the more I go to the right, the stronger it gets. In the center, they together work together, because remember how vectors add up using triangle properties. So that's the pulling away forces, like so. And other cases. So there's so many cases like that. Technically speaking, I guess you can memorize them all, but for example, this xy minus yj. Let's see what that one means. Again, when they correspond to each other, usually it's they helping each other, right? So x helps y to get larger and y helps j to get larger, but they mean the same thing, more or less. So direction and run versus rise. So usually it's either going away or going in. But now y has different sign. Let's start with x. The more I'm going to the right, the more I'm going to the right. And actually it increases with the power. The more I'm going to the left, the more I'm going to the left. Makes sense. With y, it's the other way around. The more I'm going up, the more I'm going down. When y is large and positive, negative sign forces the vector to turn around down. So it's like so. And then vice versa over here. But how do they correlate with x values? Now imagine it's a water and you have a paper boat. Yeah. You drop it over here, it will go down, get caught by this one and go to the right. And that's how those parabolic, hyperbolic tensions show up, like so. I usually imagine something floating in the air. If you drop it, where does it go? Or water, like so. While here it was all pulling away. And then here, again, if I drop, these ones add up together. So when you figure out this direction and this direction, whatever is in between has to be something both. So going to the right, up, left, how would you figure this out? By this kind of rotation. Going to the left and then right, but also down, how would you figure it out? Like so, and it should make sense. So if you drop the ball on the water, it should whirlpool like so. Okay, people posting good videos, so definitely watch these videos. Let me post it as well. I actually have some materials collecting for you in the forum. So I'll add this one. Thank you. Oh, that's not one. Nice one. Can you post it here in the forum? Oh, I should make exam links. I think for this last chapter, it's very good to find good links. Some more people explaining it better than others. Okay. I actually know what I explain better than others, and that's not vector fields. These ones are nice to have some good visualizations. So that is good. I explain well the calculation ones, and those are, this is good what I wanted to show. Yes, and those are Flux, curl, green theorem, those things. Yeah, let's do this. Calculations will be very nice on the test. I actually like this a lot. Those are my favorite problems. For example, find potential function. Those problems are really good, and I will explain you how to do it fast right now. Find line integrals. I'll explain you how to do it fast as well. Let's do line integrals. Yeah. Line integrals, actually potential function, I think, goes first in the chapter. Line integrals. Gradient field. The S is huge square root thing. Surface. Line integrals, I would not call them simple. Usually people don't like it. But these functions. Curl and divergence. I think these topics are usually good. Usually students do well here. Because you just need to remember how to do it. Curl and divergence. You will be asked to find all of this. And the potential function. Potential function. Which is So I was choosing which one to show you. This is 13.5. Let me find it in a second. I found some really good examples to show. All of them actually pretty good. Your job is to remember how carefully to integrate. I think I found some flux. And then for which field? Yeah, potential function. Yeah, let's do this one. That's a good one. Example. So we give you some kind of field with 2 or 3 variables. Be careful with that. 4x plus 5y I plus 5x plus 10yj, like so. Then, that's from your homework. Then they ask us and decide if it's conservative. A. Conservative. B. If it's conservative, they should be existing in f, small f, such that basically an integral of that capital F or the derivative of capital F gave me small f. So they ask you to integrate. First, you have to figure out, and that's the thing, you kind of don't have to actually, you have to figure out if it's conservative or not. Of course, you will waste your time if this function doesn't even exist. How to figure out A. Solution. And this is the one I like a lot. So conservative, do you remember what it means? Conservative, it means if I find this cross product, it should give me 0, 0, 0 vector, right? That comes from the topic of divergence and curl. So that's why you will be asked to find those separately or answer those questions. How to find that? The formula is, this is a notation. So as you understand, that is called del. Del usually means something like so, but doing cross product, they decide to create the notation of the determinant of the 3 by 3 matrix, I, J, K, and then instead of putting the long description of derivatives, they just decide to create representation of those derivatives with the notation del. It's a very common mathematical idea, actually, and physicists also love that. It's a short notation for partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. Because separately, del, I don't know, a function g, will be just collection of those partial derivatives. dg with respect to x, dg with respect to y, dg with respect to z, like so. So, just think about that, but okay. The third line will be your function f. The function f has two components. The third component is missing, which means 0 plus 0k. So, very interesting. Do you understand this actually? It is a 3-dimensional object that depends on 2 variables, x and y. So, a human being is a 3-dimensional object, depends on 2 things, temperature of the body and this quantity of inside of the lungs, for example. So it's possible that it depends on 55 variables. That's the correlation between dimensions and variables inside of those dimensions. The first one is 4, I should do it bigger. 4x plus 5y, j derivative with respect to y, 5x plus 10y, and k derivative with respect to z, 0. That's determinant. Let's do it. And you remember how to do it. Plus, minus, plus. Remember, that's the important part. It actually have more signs, but we never teach you in this class because we don't need them. You only need to multiply I. Then remember bombarding like so. Cross product between whatever is left with a negative sign between. And it's not a product again. It's notation. Derivative of 0 with respect to y. Well, derivative of 0 is 0. Minus derivative of 5x plus 10y with respect to z. That's notation. It's not multiplying. It's a very neat notation. Some students remember the formula, and if you know what I mean, you know what I mean. Which one goes first? As a person with bad memory, I never memorize the formula. I actually always write down the determinant and just do it fast like that. And I feel good about this. Bombarding, but this one will be negative. Remember that. This one is negative based on the formula of determinants. Minus, open parentheses. Whatever is left, determine, well, that's 0, just give it 0. Minus derivative of 4x plus 4y with respect to z plus, and the last one, bombarding plus k. And this will be the full derivative of everything. So you can short notation, you know, like so, 5x plus 10y with respect to x. That's a partial derivative with respect to x. Nice short notation if you don't like this d thing. And then 4x plus 5y with respect to y. Okay, so this topic somehow I like, even though it's tedious, somehow I like it because I know how to create it and I know how to calculate each part. I, 0 minus derivative of 5x plus 10y with respect to z, that is 0 because there's no z variable there. So the whole thing is 0 minus 0 minus. So don't forget open parentheses, put minus again. 4x, 0 again, 4x plus 5y with respect to z, 0 again, that's so dumb. And then, well, actually, oh, it's not dumb, I'm sorry about that. It should be 0, we're actually expecting that. That's what I said. If we want to have conservative field, then it's better be 0. And then derivative with respect to x here is 5, with respect to y here is 5. 5 minus 5 is also 0. I, j, k. 0i plus 0j plus 0k, plus or minus. Conservative. So that's all processes just to check out if it's possible to find the potential function. Again, it actually takes lots of effort to find the potential function, so it's very common to first check if it exists. And that's where pure math comes in. It first checks if whatever you're doing makes sense. B, find the potential function. Potential function is basically antiderivative, such that gave you all of those derivatives. Let me check the questions. So the final two sections especially confused me. Is this previous topic? No, capital F. Oh, you're right. Capital F is antiderivative. We're looking for a small f. Capital F was differentiated. Yeah, you're right. See, small f here, what antiderivative gave me this result with respect to each variable? Good catch. Yeah. F. We're looking for small f such that gave me the capital F, which we recorded. Yeah. The idea in the application problem is For example, you recorded all the derivatives with all the directions. For example, if you have a device that records magnetic fields in space and there's several planets and they showed you those magnetic fields, those are derivatives. That's the thing. They just show you, you don't see magnetic fields, for example, as a human being, right? Your device recording that something is dragging you over there. So that is your capital F, and those are derivatives. And then you want to see the whole magnetic field. You integrate it, and now you see, oh, that's how it looks like so. Make sense? So, or other way, yeah. It's actually common that we first know the derivatives of something than the original function in application problems and in science in general. Okay, let's find F. F, so capital F was given. You write it down again, and I highly recommend to do it again because you will have several of them. So write it down not to mix up one with another one. Like so. You will have ABCDs there. I saw it, some of you at least. Then we want to integrate with respect to each variable, right? One by one. So when I'm integrating with respect to x for x, some students write it down like so. So I'm thinking, should I write it down or not? Usually I don't do it. I just write down that this is derivative with respect to x. This is derivative with respect to y. So now I'm looking for the original function, and it's the integral. Just remember integral with respect to what? X. So it's going to be 4x squared over 2 plus 5xy. Agree? Agree. Then plus c. That c is not a constant. It's actually a function of the other variable we did not use for integration. And then your video in the book explains way too complicated. So I will show you the easier way to do it. Then the derivative with respect to y is given as 5x plus 10. When you integrate with respect to y, it will be 5xy plus 10y plus c. That's not a constant. Now it's a function with respect to function depends on variables we did not use yet. So check out how simple it is, much easier than what they show in the videos. We're kind of overcomplicating things. Collect the terms, let me even write it down. Collect terms with no repetition. So people who watched my lecture actually saw that phrase there. Collect the terms with no repetition. You don't have to do anything. They doing in the videos that you way too many calculations after this. So just mix and match. Do you have, so let's see, do you have 4x squared over 2, which is just 2x, anywhere else in this function? No. Okay, put it here. Well, you put it anyways, and then you match it if it's doubled or not, with no repetitions. Just don't repeat second time. And actually, that's not a vector, it's a function. Then plus 5xy plus, so that comes from the first derivative with respect to x, and this comes with the derivative with respect to y, or integral. Are we putting 5xy? No, we don't have to put it second time because it's repeated. Did we put 10y before? No, so put 10y, done. That's it. The overthinking it in the, also it's squared over 2. But that's a different topic that I just messed up. But the idea is how do you collect them? Yeah, I just noticed. 10y, I lost the y, so it will be y squared over 2, which is 5y. Yeah, squared. But the point is collect with no repetition. I think we do it way too complicated. Yeah, I noticed as well. So review these problems. I think these are really good. It's very nice if you don't mess up calculations because these problems are just nice and just good problems. Now let's practice finding in general those things called del and interesting question, actually. You remember that if they give you initial condition, then you also can use it if needed. Sometimes they give you, oh, but also function is 0, 0 or 0, 0, 0. Yeah, technically speaking, it is also plus c over here. This c can be something else, but this is difference of the question, what is requested. If they ask for potential function, this is a potential function, one of infinitely many potential functions. That is a very correct answer, actually. If they ask you for exact function, then you have to claim from them, which people who create the problem, initial condition, for example, f or a 0, 1, and 2 should be better be something like 110. Then you plug it in, get that thing, or maybe 110x and stuff. And that's how you get the exact solution for the exact initial value problem. So, no, it's just one extra step, but actually it's not too bad. Okay, let me think for a second what I wanted to show now. Finding del and curl. We just did it. So your job is to know the notation, I would say. What does it mean? So one is just collection of derivatives. And the other one is this determinant we just did. That's potential function, but now a different problem. So same thing, but this way. That's also the topics of Green theorem. I'm not jumping, it's kind of connected Green's theorem. If f is given, you can actually use Green theorem to check as well if the field is conservative. Conservative vector fields are good fields, and by good fields means we can integrate them, and by that we mean we can find a potential function. So A is f conservative. We can use this p differentiate with respect to y, better match with q with this differentiate with respect to x. That comes from the Green theorem. What is what here? Notation is f, first is p, then is q, like so. And that is derivatives of small f's. So p is 8x. It's too much writing, so usually I just take a pencil and write down, this is my p, and this guy is my q. Let's find p with respect to y. You always do the other way around, the other function. It kind of has connection with xy being the same as yx for good functions. That's the same idea here. They should be the same. And that's why you sometimes see in the book they're saying that this should be 0, but it's the same thing. It means they're the same. So let's do it. Derivative with respect to y in this case is minus 8x sine y minus cosine x derivative. You see, your brain's supposed to be good at jumping between differentiation and integration. We just integrated with respect to each variable. So now your brain should be good enough, and I guess awakened enough with coffee, to differentiate instead, or else you might mess up. With respect to x, but second one, minus 8x sine y minus cosine x. Also, I wanted to point out, this is in 2D, and this is in 3D. So it took us to third-dimensional ideas here. Well, they're the same. Good job. So conservative, yes. And now you can do the same thing as just we did before. Integrate each part, but now your brain should go back to integration and integrate correspondingly. Integrate p with respect to x and integrate q with respect to x and collect terms with no repetition. Remember, we're not going to give you complicated integrals. So if you start doing some integration by parts, well, actually I should check if what I'm saying is correct. I think I'm correct. Then it's suspicious. You're probably overthinking it or don't do the correct partial integration. Now, Mr. Pretender. Okay. Finally, is that all I wanted to show? Actually, it is. How do you feel about these problems? Kind of those are my favorite ones. I think I wanted to show del thing, but let's check. They're just finding divergence and curl. Like, can you just find that? Divergence and curl. Let me write down at least the formula. In general, divergence of f and curl and curl of f. Review that. Divergence just differentiate. Basically, curl we already did. That was that crazy. What is divergence? Who remember? Just kicked me out. Fine. Who remembers what is divergence? Exactly. It's a sum of all. That's a very interesting idea, that gradient, if you remember, which looked like so. Nice triangle gradient f. That was a collection of first derivative with respect to x, second, first derivative with respect to y, first derivative with respect to z. And that will show us how strong the gravity, for example, goes to the x, y, or z directions. Divergence takes this idea to the new level and adds them up together. It adds the strengths of all of these derivatives together. So you find derivative, well, okay, let's do p, q, and z. No, what was r? Yeah, r. P with respect to x, and add with q with respect to y, and add r with respect to z. Very interesting idea. If you can imagine, there was an interesting image I showed in class, in my classes, when there was a mom trying to do shopping, normal grocery shopping, and then she had 3 kids. One wanted to go and was dragging her hand to the toy place, and it was toy shop. The other one saw arcades to play, and the other one wanted to go to the restroom. So they all had different strengths. Those are derivatives, and they all were taking in different directions. So where will she be pushed? And will she be strong enough to stay in the same place? So that is a very cool idea that they add up together, those vectors, I would say those forces. And then the total gives you information of what has happened. While curl is this determined, and we already reviewed that, so I don't have to go there. Determined, and it has lots of explanations. We kind of told you. Curl actually explains how much things are curling around. The Whirlpools. That's why it has correlation with the title. And then there's a big curl, like small curls. If you listen to my lecture of the last classes, I actually explained really well how small rotations, and you drop the ball. If you drop it here, it will just stuck over here. If you drop it here, stuck over there. But total curl actually exists, right? If they all small whirlpools circling this direction, which is counterclockwise, and if you drop a big ball or lots of balls, they all will go around. So imagine a sink with small whirlpools, and then all of it will have a huge whirlpool. And moreover, in the ocean, it actually happens. Some unexpected whirlpools show up from the currents accidentally getting close to each other, and then it's creating those rotations. So that is pretty cool. We never actually explained you before this chapter the quantity called rotations, how much things are rotated. We did how much things are perpendicular to each other, how much things are parallel to each other. Those are dot cross product, remember? Then we did surface, how much things are smooth, and then closed paths, and then how much things are away from each other using three-dimensional IJK components. So we never actually found, or we also did how much things are stretched and compressed. And this is the one that explains how much things are curled or spiraling. So that's why it's the hardest topic, because that's exactly explains the hardest components of the physical qualities of swirling around or rotations. That is a pretty cool idea. Gonna make 2 examples. Let's see. Yeah, surface integrals, I think, are annoyingly complicated. So let's do examples on that. Let's do examples on 13.2. Let me check my notes. Green's theorem. Vector fields are perpendicular to the line segments of the curve. Okay, good. Line integrals. Curve. I did it. Okay, good. Line integral and formulas. This is the annoying one. Line integrals. It's very important though. But as many important things in math and physics, it is complicated. You need to know the formula. Integral over C f dr. Looks so simple, like how it can go wrong? And then we give you f, we give you r, right? And then we ask you to find this line integral. So I have an example here. Let me write down this example. What are your steps? Step 1, remembering the formula. They will be simple formula and complicated formulas. Let's see in this case. Simple one is remembering that this is integral from A to B. F, you plug in your R, which was given. That is called parametrization. Parametrization process. You plug in your R, which actually depends on a third variable T. Third, fourth, whatever variables we have already, way too many, times dr, but remember that dr means derivative of r. So multiply by r prime with respect to t dt. You don't have to memorize this formula. To be honest, from the look of the first formula, I can tell you that that is exactly what it means. It means find line integral over the vector field. F is a vector field. C is the path. So background idea behind this, you will see it like so. For example, I will finish writing right now. Find, so this is field, right? R is a parametrization of C, where C is your path or curve. So what we're doing here is we're finding the integral above the curve. It's basically a fence, like so. We actually never done this before. We only find integrals between areas in calculus 2, in calculus 3 volumes and stuff. But what if this is just C, some kind of line, and called line integrals? So R describes our job, our job. The job of the R of T is to describe this field. I like to show in class, you take a laser and actually bring a laser pen, and then you describe with your laser like so. Oh, it's going like so, negative or positive direction. So that's why it's called parametrization. It's literally, its job is to describe the path. So find the work done, the work done. What does this have to do to the work? By the force field F, and they give you F, X, sine Y, comma Y, where? So again, what does it have to do with the work done? That is a very cool way to explain, is you're moving through you're running on a track or marathon, but there's a very strong wind. Very interesting idea. Will wind help you? Will be against you? Or will not make any difference with your running? That is exactly what they're saying here. It's a force that either it's behind you and then it's helping you to run faster, or it's against you and now you're slowing down, or it's somewhere perpendicular, so you don't care at all. It's just like perpendicular to you, you barely feel it. So here's the force. This is the wind that was recorded. For example, it's like so. So the wind is keep being recorded, but you're running through this wind, maybe like this. So direction matters. And then you are the moving object. In moving an object, right? Along where? And that's why a curve matters. Because if you're moving same direction, then it will be helping you to move. If you're moving back against you, if you're moving both back and forth, you know what's going to happen? You'll be collecting all the forces together. The curve is 1 equals x squared from 1, 1 to 2, 4, something like that. So if the wind is changing, that's the wind. It's going left, right, like so. So it's like very typical wind, I guess. It's not always flat, straight. And then you're running maybe like this and up. Well, actually, in our case, it's a parabola, as you can see. So it's very realistic, down and up. On the way, while you run, you're collecting those forces of the wind. Some of them are helping you, like over here, for example. They're helping you to move faster. Some of them are perpendicular to you, like over here. They don't give you any changes. Some of them are against you, like over here, for example. They will be in your face. You collect them all. If the total result is positive, then the wind was helping you in total. If it's negative, the wind in total was against you. If it's 0, nobody cared about the wind. So your job is to figure this out. So F is your force. Integral F dr exactly gives you the work done. That's one of the applications of the line integrals. The work done of what? Of the wind F, and wind is just an example. You can imagine gravitational forces in space and stuff. On C. Step 1. If you have your R, you're lucky. You can finish faster. If you don't have your R, you have to create R. So parametrization. Parametrization means you need to build your R. You sketch the graph really fast. And by really fast, you just hope that the graph is easy. In this case, it's y equals x squared. Then they say that x is moving from 1 to 2. Find 1, find 2. Y is from 1 to 4. Makes sense because it's in the parabola. Like so. So this is the only path we're describing. And now we know that it's going from top to bottom. Might be going backwards. You need to check that. One of the ways to do parameterization is to call x t and then y whatever happens with that t. So you call x to be t and y will be plugged in. Not much. Plug in. That will be t squared. You can ask what the heck, how did we know it actually be t? Yeah, it comes from experience. You can make lots of examples. And after 100 examples, you notice patterns. Of course, there's some classical parameterization like x equals r cosine theta or t, r cosine t. R sine t is for y. There's a classical for lines. This is one is classical for parabola and lines, actually. X equals t and then y is whatever y does. T is between what and what? Let's see. Since x is between 1 and 2, t is also will be between 1 and 2. This is r. If you see that, you don't. So I remind you, r is created from x and y, but just each depends on t. Not necessary. Sometimes it's theta and r and stuff. But whatever parameterization you use, that's going to be your r. In this case, r is x and y. So it's a vector. Not only it's x that depends on t and y. It depends on t. But it is also now t comma t squared. R is t comma t squared. Again, you're lucky if you're given r. And in some examples, I noticed they do give you r. If not, this is the first extra step you have to do. Let me see if you have questions. That is the hard step. Oh, okay. Suspiciously quiet. Either it's really good or really bad. And now starts, so this, you skip the step if R is given. So let's assume R is given now. Well, we created it, so it's fine. R is t and t squared. You take this R, step 2, plug into F. Okay, go. Let's go back and check. What is your F? F is, I'll go back here. F was X sine, that is the recordings of, for example, gravitational forces, or the wind, basically. Oh, the wind seems like working as a sine function, which makes it wavy on the x-axis, or the first component, and then growing up or down on the y component. So that actually makes sense. It's literally like wind and stuff, so very makes sense. And that's why we don't know exactly if it will be helping you or not. So you are running on this part of the parabola through the wind that was recorded like so, or through the gravitational forces. Plug these things, which are x and y, into F. F will be x is t, sine is y, but that's t squared, comma. And then y is t squared. Now you have your F in terms of t. Again, that's going to be the first step if you have R right away. Step 3, what is missing? The derivative is missing. Why do we need to have the derivative? Because of the formula. Formula says F, where is it? Formula says F dr. dr should remind, so you have his F. C will figure out C, but dr, you never differentiated R. So you can differentiate right away if you want, right after you build it. dr will be derivative of t is 1, derivative of t squared is 2t. That's derivative of R. Are we ready to build the integral? Yes. The force or work done, actually. Work done, or just the integral in general. There might be no backstory behind this. They just give you stuff and you figure out. Over CF dr is, if you want to remember the formula, it's from A to B, F with the plugged R inside times R prime. And since you differentiated R, now it's dt. But I don't remember this formula. I remember that F, you should differentiate R and then plug R into F. So F is t sine t squared, comma, t squared times 1 to t dt. And since we have 2t, no, and since we have dt, we should have it in terms of t. T is running from 1 to 2. That is a scalar product, which is dot product. But if you remember, in rational way, we call it scalar. Scalar, this name scalar reminds you that the answer better be not a vector. It's better be a number. In this case, it's a function, not a number. But basically, it means you multiply component by component. That's a simple case. So it's going to be integral from 1 to 2, and you have t sine t squared times 1 plus 2 multiplied by t cube dt. Integrate each, plug 2 and 1. Let's actually use substitution, I can see over there. And you get the answer, which is 1/2 cosine 1 minus cosine 4 plus 15. That's my notes. How do you feel about that? It's like Rick and Morty says at the very end. Did you get any of this? So that's not all. Don't get relaxed. Let me see. Vector fields, vectors are perpendicular to line segments. Let's talk about running through the wind thing. What if they're gonna ask you to match the graphs again? So Swifty, yes, Swifty, that's true. So what if they ask you to match the graphs again? Vector field. So vectors are perpendicular, I'm skipping on, to the, and I'm skipping the, to the line segments of the curve. What the hell does this mean? Oh, if and only if, that is notation for if and only if. So it goes to the right and to the left. Line integral is 0. That's why it's part of the line integral topic. Like line integral is 0. What does this mean? So let me give you an example where it's really makes sense. Like so, you are running through the wind from here to here and back. Actually, you can always imagine back, doesn't matter. You're running on this little piece, but the wind, oops, the wind, I don't want to do like so. Those are the vector fields, right? Why did you change color? Yeah, it's overheating again. Interesting. The wind is like so. Does it help you? Does it get against you? It's over in the air, you don't feel it. How do I know? Because vectors are perpendicular to you. So they're somewhere above, you don't feel them, and so you don't care, so you keep running. This is a good example where the integral is 0 because the work done is 0. It doesn't do any work against you or helping you. However, Flux should go later. Yeah, that's the Flux later. However, if, to review those kind of homeworks too, if you're moving along, let's do again, like so, like so, like so. This is like a very typical swirling wind. So going down. However, if you are moving, change the color. Coloring is important here. Okay, I did it. 5 minutes later, I changed the color. Like so, then you see it's helping you most of the time. Maybe you even not start here. Say you started here running. Oh, that's a good example. You started running up, then changed, then up, because that's your track in the park. And the wind is swirling. At some point, the wind was in your face. And you're like, oh no, my haircut, you know? And then the work is negative because it's in your face. At some point, it was perpendicular over here. Then you did not care. And then slowly it was following your direction, not so much, but then more, and then you totally was going with the wind. So your wind was in your back. What is the total? The total is positive. So it means wind was helping you. That is the idea, because you was moving totally in the same direction. And the tricky example. I kind of find this pretty entertaining, fun examples, but is it the same? Those circles, again, those are not circles. You should do lots of vector stuff. I just kind of too complicated. So the same swirling idea. And now you had a complicated picture. Change the color. You start running up to the left, up, going back, like so. Very interesting. So it might be 0 because Yeah, if it's the same, like it should be very the same or not. If this was helping you all the time, and then this was against you, and these are the same, they will be canceling each other. This was perpendicular and this was perpendicular, so nobody cares. So it's very interesting how you see. If you see that this one is obviously larger, then the total will be positive. So that's one you should figure out on the beautiful graph, not my graph. But this is the idea of the field helping you or not helping you or ignoring you because it's perpendicular. So as always, remember that perpendicularity has some connection with zero product. That's exactly what it happens over here. This product gives you 0, so it means there is no number to be positive or negative. So it doesn't add up to the total work of the field. That is the idea here. Yeah. Nice. Finally, we are going to the flux. I think we did not do flux yet. What the heck flux is? I think that's the final. I prepared something here. Let me find it. I prepared something here. Oh, and also the square root. Oh, that's the flux. The square root thing. Consider the integral. Find that. Well, compute the curl. We did curl. So where was the flux? Flux is the very end, I think. Directional derivatives, that's not going to be there. Surface integrals will be right now. Surface integrals. Flux. Very good. And the formula. Let's do that. Evaluate the surface integral with the given vector field and the positively oriented surface. In other words, find the flux of F across S. So finally, we're getting to the hardest part of the chapter is surface integrals. That's definitely going to the 3D of 3Ds. Line integral is integration, this curtain. Remember I showed you the curtain? There's a more beautiful picture of the curtain, but this is exactly what you should see in 3D. Again, check my videos, I actually show very nice pictures there. I can actually just show you here. Line integral is the fence. Like so, see? Very beautiful. Should copy that instead of what is this? And I was choosing between math major and art major at some point. What's this ugly drawings? So I chose math major. Spoiler alert. It was a beautiful fence, the area of the curved surface. So we never done it before. In even calculus 2 was not enough information to teach people how to jump from something simple like this, which we do in calculus 1, to integrating over the line. Think about that. But now we're doing flux. Let's do surface integral. Surface integral. That is integrating over the surface. So we keep increasing the dimensions all the time, as you can see. Line is one-dimensional thing. Surface is not one-dimensional, two-dimensional thing. Surface is three-dimensional thing. So now we're integrating over the surface. And that's why the formula becomes so complicated. And that is why when they ask you to find evaluate the surface integral with the given vector field, it looks like this. What if it's also a vector field now? We're not just running through the park using one line. What if it's the whole surface we are running through? And that's why you should not imagine running anymore. What if it's magnetic field going through another magnetic field, or heating or something like that? So that's why it's more complicated, because we're increasing dimension of on what we are running. And through what we are running. Well, through what we're running is the same. It's still vector field, but we increasing the dimension on top of what we are running. And that makes sense, basically. The higher you go, the more interesting it gets, but it's more complicated as well. So let's write down this problem I want to work on. And that's the last formula I think you need to remember. I think I covered all the formulas already. Find the surface integral. I'm skipping the surface. Seriously, just change the color. Surface integral. And double f ds over, what's the notation? I don't see, it's too small. S, I think. Yes, I remember correctly. S. For the given vector field F and positively or negatively oriented, blah, blah, blah. So check at home the sign. Orientation matters now since there's a surface. Here's the idea. I'm showing you on the camera. The surface can be. Line has a simple orientation. Let me first explain the line situation. When we just had a line, it's again a two-dimensional object, even if it's in 3D. On the line, you can either go from left to right or right to left, which is positively oriented or negatively oriented. That's all. Surface, though, it's more complicated. Surface has positive direction and negative direction down. So it's very important. So your skin outside of your hand is a three-dimensional object. It's a surface. Has positive orientation going outside, but skin has an inside surface as well. It's going inside towards your bones, and that's where all the vessels are and stuff like that. So it's phenomenally interesting to actually understand surfaces orientation, and that's where at the end I will show you rare objects which have only one surface orientation. That's all. And positively oriented. So guess how did they decide to check what is positively oriented and negatively oriented? I already gave you the idea with putting a pencil away from my skin. That is a normal vector. So if it's sticking outside, positive, inside, negative. So it makes sense to use normal vector to judge. But also there's a rotation, if you remember we did rotation. That was for vectors and stuff. Orientation, positively oriented. That means IA, IE, for example. No, IA, find the flux of F. Flux has so many applications. If you ever actually go into these topics in upper level courses, you will be definitely amazed by how many applications it has. So we give you F, and I'll tell you in a second, X, Y, Z. F is 4xi plus, as the comma, 4yj. Well, then you don't have to comma. Yeah, that's the plus 4zk. And now you change the color. Okay, that's very late. S is sphere. So flux actually describes, for example, the blood flow in your vessels. That makes sense. You heard this phrase before, the flux of some movement, water movement and stuff. So when you squeeze your vessels, the flux becomes different. When there is a blood clot, the flux will show you that. That's exactly the integral over the surface with the field introduced. So if there's a blood clot, the blood will be going around the blood clot, and that's how tumors will be created at some point, and so on. Heart attacks, I mean, and then tumors also show up and create tension. So flux can show that. And also you'll be surprised, but there are equations called traffic equations, which model traffics. That makes sense. The same equations that model traffic's behavior model blood behavior, because blood cells, if you zoom out, just look like cars. And then if there's a traffic, which means there are way too many of them, and then you have the fat piece That's why you're supposed to pay attention on cholesterol, right, levels. Then this traffic has to go around. That's all a representation of some kind of construction going on or police standing. So lots of cells have to now squeeze in over here. The same equations describe blood flow as just like as traffic flow. Pretty cool. Let's do it. Step 1, know the formula. If you don't know the formula, you can scroll the problem and just accept a 0 for that. The whole point is to remember the formula, which is kind of complicated. This formula is hard to remember. So, and there are two formulas that looks the same. Let's introduce both. One formula looks like this, double integral over S, f ds. And the other looks like this, double integral over S, f ds. Isn't that not confusing at all? And they are different. This one is double integral over d, f, plug in your parametrization, which is r as always. But now r depends on u and v, multiplied by the size of the result of the cross product, which is a vector, so that's a magnitude. Derivative with respect to u of r and with respect to v. That's basically a normal vector, if you remember that. du, dv. What is going on here? Where the other one is double integral over d, capital F, plug your r as always. So we perform parametrization using u and v times not the size anymore, just the cross product, v, du, dv. So which one is which? That's the confusing part. We need to know the difference. The first one is surface integral. There's no vector field introduced here. So it's just integration. It's also corresponding to line integral in the previous topic. Line integral just exists by itself. It's not necessarily represents any running through the wind. Line integral, if you remember, was a beautiful area of the fence, just the area. Same here, surface integral, let me write down. Surface integral is just the result of this integration integral, which represents stuff. The second one actually finds the flux, which means now the surface integral has some F introduced. F is the vector field. So it will be surface integral, but with capital F, integral of F. And basically, if you see F was given to you, capital F, the field, then you know that you should use the second formula. Formula number 1, formula number 2. What else to mention here? This is ds. What the heck is ds is this area of the parallelogram. So we learned it at the very beginning. Ru, Rv, cross multiply. The size of the area can be found with magnitude of that cross product. While the second integral is normal vector, includes normal vector. So it's not the size of it, it's actually the normal vector. Very simple, right? That's why the last topics usually definitely upset people in this class. I clearly remember that. So try your best. Try your best. D is your object. In this case, our D, so S is a sphere. So let's figure out what the heck the sphere is. This sphere, so solution. If you see F, E, U, C, F, which is field, vector field, then use formula number 2. They literally asking you what is happening with U and lots of other people. Yeah, marathon, people running together on the surface. The total work of the wind over all of you guys. That's basically blood flow if you think about it. That's the flux. So surface integral over the vector field. Flux. So if you use the term flux, they mean formula number 2. How to parametrize, if you don't have any, the sphere. We know how to parametrize, that's very ugly sphere. The sphere. X equals rho spherical coordinates, and that's very nice that we already reviewed them right now. Rho cosine, rho sine theta. Remember, that's how I remember it. And then for the 3D case, which is sphere, not polar. Polar is a circle. Sine phi, since we did sine and never did cosine, let's do cosine phi, but I forgot to multiply by a rho last time. Then they told us the radius, did they? They actually are supposed to. Rho cosine phi. Did they mention S is sphere? Oh, they did. I did not write them. S is sphere. Please finish writing down. What kind of sphere? X squared plus Y squared plus Z squared equals 2. That is the sphere. That's very nice. A very nice sphere. Center to 0. 0 radius square root of 2. So I'm not going to change anything except the radius square root of 2. Everywhere you see rho. Let me wait for a second. Square root of 2, square root of 2, and square root of 2. That is my sphere, which is given here. Now we will have formula number 2, double integral over d. F, let's plug our r. What is our r? That is our r. R is combination of x, y, and z. X, comma, y, comma, z. So we will be plugging this r into F. Everywhere we see x, y, and z. Then we will have to figure out cross product of those partial derivatives to find normal vector, du, dv. So sphere also was not in any way restricted. So we know it has complete rotation with theta and complete rotation with phi from 0 to 2 pi, from 0 to pi corresponding. Nice. When you have parametrization, maybe start with derivatives right away. Maybe previous steps also easier to do right away. Differentiate with each variable. What variables did we create? When they mention u and v, you could ask me, what the heck are they talking about? What kind of u and v? U and v will be different variables depending on the case. In our case, what are u and v? U is theta, v is phi, because as you can see, they are changing because this is how the sphere is rotating. But radius is fixed, it's always square root of 2. So let's differentiate rho with respect to theta. I'm looking at x variable first. Square root of 2 minus sine theta, sine phi. That's not it. We're differentiating the whole, not rho, r. We're differentiating the whole r, comma. Remember, it's going to be cross product. Cross product is a vector product. To have a vector product, you should have 2 vectors. So don't do plus, don't do a function, it's a comma, comma. Y with respect to theta, looking over here, square root of 2 cosine theta, sine phi. Z with respect to theta is 0, there's no theta there. And then with respect to phi, repeat, square root of 2 cosine theta, cosine phi, comma, square root of 2 sine theta, cosine phi, comma, minus square root of 2 sine phi. Those are your 2 vectors. Find cross product, then or thus. R prime with respect to theta, cross product, which is a vector product, will be, remember, the determinant from exam 2, I, Jake, or exam 1, Okay, plug, 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 plug each vector. That is very fast. You just do it. I'm very skeptical about this. That's a lot of work here. And then guess what? You will have to integrate the result of that. Moreover, we did not plug anything into F yet. Let's do that. So that will give me a vector. Remember, that will be a vector. Now, step 17, step 3. F was given in terms of X, Y, and Z. That is no good. For the integral to be all in terms of theta and phi, we have to fix that. So you take your X, Y, and Z and plug in. Let's do it. Basically, you plug in your R. 4 times X. X is a square root of 2 cosine theta. It's times sine phi, comma. 4y is 4 square root of 2 sine theta sine phi, comma. 4 times z square root of 2 cosine phi. That is the second vector. Why I'm talking about second vector? Because step 4, you need to find a dot product of this vector we just built, depending on the one that depends on R, times the result of the step 2 cross product of partial derivatives theta with respect to theta and with respect to rho. The result will be not a vector anymore. It's a scalar product. And then you integrate that stupid function. So the result of that product will be you multiply corresponding components and add them together. The integral f of r, the integral, double integral, f of r times r theta, r with respect to theta times r rho, d theta, d rho. Let me know if you don't understand where these came from. I'm changing the formula we had. Instead of du dv, now it's d theta d rho over d will be double integral. Double integral. The result of that dot product we just did should be a function. And the function is minus 8 square root of 2 sine cube phi. Makes sense. There are lots of signs there, so they multiplied and it became sine cube. Minus 8 square root of 2 sine phi and cosine square. So something cancel out. Apparently, that's good news. D theta d, doesn't matter, d theta d phi. And then we agreed, since the whole sphere was not restricted by anything, theta is from 0 to 2 pi, phi is from 0 to pi. Don't mix up these. And then you finish integration. I don't even see any integral, anything in terms of theta. That gives me 2 pi right away. So that's how you can speed up at least some kind of calculations here. This integral in the red is 2 pi right away. And then your job is to integrate from 0 to pi, all that kind of stuff with respect to phi. Look how smart I am. Thinking very hard, and it's 32 pi squared of 2. I'm so proud. That is the answer. Cross rho, let's see. Isn't r theta cross r phi theta and rho? No. Good question. If you have theta and phi. Oh, I see. The function isn't, yeah, you're right. The function is in terms of, see, I'm getting too tired. theta and phi. So derivatives will be in terms of theta and phi. Theta and phi. Good catch. And then what is this rho? Rho is a fixed number. It was squared of 2. So it makes sense. It should not be inside of the integral. Yeah, good catch. Now let's see if this is all or not. Surface integrals. Let's do this one. When there's no flux. Yeah, let's do this nice example. Example. If you don't see capital F, then you don't need capital F here, which doesn't make it easier too much actually. They just give you this F. To zoom in to see what is happening. Is it x squared? Just okay, I have to figure out from the answer. X squared y plus z squared. Just a second. Gradient. Direction. No, we don't need gradient. ds. Okay, fine. Let's keep it like this. So if they have like so, and they gave you x squared y plus z squared ds. S is a cylinder. Cylinder x squared plus y squared equals 9. Between two planes. Yes, I remember this problem. Between two planes. Z equals 0 and z equals 4. That means there's slicing a cylinder. Cylinder is infinite unless you make a lead and the bottom. So 0 is the bottom and 4 is the lead. So it actually makes sense. This is formula number 1. How do I know? Because I don't see any F introduced. There's no wind, no gravitational forces and stuff like that. No blood pressure and stuff. So integral F of R, don't forget to plug your R, which we need to build in this case. And now find the magnitude of this cross product, which we did last time. We never found the magnitude, so this time we will. Step 1, solution. Let's create parametrization of a cylinder. We remember that one. That's where we learned these guys before. 3 cosine and 3 sine. Who's spelling? 3 cosine and 3 sine, and then z is just z. Z is growing infinitely up and down. But in this case, it's not growing infinitely. It's actually restricted. This is your R. R is the collection of x, cosine theta, sine theta, and z, where z is running from 0 to 4 because of the slices, and theta is the full circle of the cylinder. This picture is looking very nice. It's not necessarily a right circle, cylinder. It might be tilted away. But the whole rotation here, I know it's the right cylinder because this is a perfect circle. It's not ellipse. Yeah, actually still might be tilted. But anyways, and then from the planes, 0, z equals 0, and z equals 4. Like so. Very fast. When you have your R, you are ready to go. That was like extra step. So now, step 2, immediately find derivative with respect to the variables you have. I forgot to plug z. Z is z. Yeah, what kind of variables do we have? We have definitely variable theta, and then we have variable z. So it's very interesting. Apparently, radius is fixed. Height is changed. So how would you describe all this object? You would be changing the height. That means z is a variable. And then you will be keep rotating. That is your theta. But how far you're going away from the center is fixed. That is the radius 3, which I missed over here. Derivative with respect to that, derivative with respect to this. I would just skip this step and start building the cross product right away, because you need to write them down over there anyways. I, J, K. Now write it here instead. Derivative of R with respect to theta minus 3 sine theta That's the first component with respect to theta. Second component will give you 3 cosine theta, z with respect to theta, 0. And then all of this with respect to z, 0, 0, 1. So you see, it saves you time. Actually, multiplying this one is not very hard to find. Lots of zeros. So cross product here gives you 3 cosine theta, comma. Next one will be minus, but then it will be also this cross product. Minus minus gives you plus 3 sine theta. And the last one is 0. 0 times 0 is 0. This is a nice example. But we don't need that. So your job is not to forget to do extra step. Find the size of this vector. Remember, vector is what? Direction, magnitude. So the size is coming from the first exam. Square root of square of each 9 cosine square plus 9 sine square plus 0 squared. That's a perfect 3. Very nice. Why do we do that? Because now we'll build the integral. Step 5, the most important one. Integral over s, f, dr. It's not capital F. Whenever we're given any field, so it's small f, has a formula. D, plug your r inside of f. Let me see if I remember. Plug your r inside of f. You still find that stupid cross product. In this case, it was theta and z, but now you're more concerned about the size of it. So you find the number instead. So you will not have dot product anymore. You have number times a function. And then d theta, dz equals double product. You have f. Did we ever plug anything into f? We didn't. So you have to plug into f. Forgot. X plug in, y plug in, z is z. That's the only convenient one. So let's do that. You can do it inside of the integral right away. F, so it was x squared y. X is 3 cosine theta squared. Y was 3 sine theta. And z is z. That's my f. Times the result of the finding the magnitude of the cross product. That was 3. D theta dz. Cylinder. So let's see. Theta is spinning from 0 to pi. Z is cut from 0 to 4. And there was a number outside? Oh yeah, there was. That's what I could not see. It was a number. It doesn't matter. Okay, and then you just integrate. And you get a number. Just because it's some kind of number. And you get a number. So you want to make sure your rotation upward. That's true. Let's see what else I wanted to show. Already above 2 hours, but it's always like this. But I think I covered everything. Let me see again. I have it open, tabs. So with these surface integrals, if they don't give you any explanation, that's what you do. Oh, the square root thing. Oh, that's what we did. In some books, they give a complicated formula with a square root. Yeah, don't memorize that. Now I can see. ds. Square root is still, it comes from the magnitude, so. Yeah, actually, let me check notes just in case. That's a huge square thing. We did this, green theorem, we did that, we checked. Work done by the field. Conservative field, we checked. Did we check conservative fields? Yeah, we did. Derivative with respect to x should be equal to derivative with respect to y. We did that. I wanted to show actually that in a second. One more time. Theorem on a circle. Cylinder, we just did that. Oh, we just did this in the same example. It's very good. I think we covered everything I wanted. So while I'm looking for, oh, I found. Okay, and it found it is magnitude FDS. Yeah, no, that's not a new formula. I don't know why they keep introducing it as a new formula with a square root. That's where the square root comes from. So that's what I don't like how they did in this book. No, I did good. I did it correctly. So remember how to do that. And then I wanted to show you this weird notation, which you probably were surprised to see. Very interesting. Totally blows calculus 2 or 1 people minds when we teach them integrals. They're like, I like to show again Green's theorem. Green's theorem is very important. It goes to 3D. And we're very upset that we don't cover the 3D case for you. We just give a sneak peek a little bit. But in 3D, it's actually even more important than Stokes' theorem takes Green theorem to 3D and upper dimensions. That's when it gets really interesting. And that is a fundamental theorem of mathematics in upper dimensions, and everyone should know. After Stokes' theorem, it becomes really cool. So we kind of, it's upsetting that we cut off here. Example, if we give you this weird looking integral xy dx plus 10x squared dy. Super interesting idea. How did mix this up? You know, never show this to calculus 1 student who just learned integration and totally messes up the whole idea behind what is dx and dy. But the idea is they collect when the fence, we're trying to find the area of the fence, if you remember, over this curve. They kind of, a very interesting explanation I heard from the friend. If there's a flashlight shining to this direction from the right, that will be the x direction. Then the shadow will be normal integral. Let's see, the shadow will be from here to here, and that is the x part. If you have a flashlight over here, he has a very nice picture in his PDF. Then it will be dy, and then versa, I think. Yeah, dy, dx, yeah, on the floor. Then it will be this one. And then collecting the shadows together gives you the area between those two, which is the fence. Pretty cool idea. So how do you do that? P. So you need to remember the notation. It's actually integral of p dx plus q dy, like so. So this is my p, and this is my q. Use Green theorem to evaluate the line integral along the given positively related curve. C consists of the line segments from this to that, blah, blah, blah. And then we found that there's a formula. Either you do fundamental theorem of calculus if you know the area, or you use this formula, differentiate each part with respect to the other variable. Find a difference. This weird thing came from the matrix, actually. Too complicated to explain, but maybe you saw it in the book. That is equals to a line integral, like so. Very interesting idea is that those are small rotations, which we keep explaining to you how to figure out the rotations. So those are small microscopic rotations. I can see in my notes, rotations. So it will show you how much things are rotating, say in the ocean. There's one rotation over here, one rotation over here, one rotation. Double integral sums them up. Sum of. And that equals macroscopic rotation, large or total rotation. So micro rotation, big rotation versus small rotation. So it kind of adds up to large macroscopic rotation. This equal sign explains that. That's what the Green's theorem is about. So blah, blah, blah. The parametrization is, we did it before. I don't want to do that. But the connection between integrals, you will have double integral, derivative of q with respect to x. Q is 10x squared. So it will be 20x minus p 10xy with respect to y 10x, like so. The x dy, dy dx, and then you figure out these guys using parametrization. That is what I wanted to explain. Sometimes you just know the area. If they say it's above the circle or a square with the given numbers, you just know the area right away. So that's a shortcut to this problem. Yeah. I think that is all triple integrals we did. Yeah, I think that is all. Let me see. People got distracted. Probably it's too late already. So, oh, do you know interesting? Let me see if I remember correctly. In the upper dimensions, how to know the orientation, positive orientation or negative orientation. Let me see if I remember. I remember it's like this. In your backyard, there's a pool. This side that is closer to the pool counts to be positive oriented in 3 dimensions. I think that's how we did it. So when you're walking around the pool, no matter where the pool is located, up, down, right to left, it's in 3 dimensions. Counterclockwise going around the pool counts to be positive direction, something like that. So it goes to upper dimensions after that. We don't need this class, but just remember that idea. This integral, I do not even define, there's a segment there and stuff like that. It's not very, it's just too long to explain, but it's just one of the many examples. So left hand rules, exactly. Now, what else? Let me quickly check. That's all I want to show. Curl, divergence, lots of pictures. So you guys wanted to keep pictures. I can keep all the pictures. I'm just going to be, they're going to be like half of the exams, to be honest, pictures. Yeah. Multiple choice is nice because it gives you partial credit. If you messed up some picture, at least some other, maybe they will give you partial credit. But I don't know. It's just, then review the pictures. Yeah. And then initial value problem, I mentioned that. Maybe I should mention here, make a note. Go back to the potential function problem. Surface integrals, flux, potential function was here. We checked, now that was work done, and flux. Line integral, here's your beautiful picture of the fields. So here's your small whirlpools versus big whirlpools. See, I already mentioned that. But the potential function, conservative, yes, find the potential function. Review by yourself. Review initial value problem. They will be, initial value problems will be hunting you in differential equation class and other classes. This is where they give you, for example, that f, no, find small f, exact one, knowing that small f is 0, 0, 0, for example, is 5. So how would you use that? That will give you C. We did it in calculus 1 and in calculus 2. It's the same thing, just taking you into 3D. So plug in 0 and whatever is state, that should be 5 and add it up. So that is important. Matching graphs, lots of matching graphs. Check that. Were you impressed with this 3D rotational stuff? That was pretty cool that someone actually coded all those 3D zooming in and zooming out stuff. And then I wanted to also mention this. I think I found it really fast. This one. I will post the link in the forum and I can go and open it. Here, one of our faculty member actually specializes on visualizations. So let's do that. Exam links. I just created this in here. Yeah, check this out. Pretty cool. So we don't do maximizing, minimizing in this exam, but I wanted to show you that it's pretty cool that if you are hiking this down, for example, you're hiking down, on every level, there is a contour map. And then as I mentioned before, see, check this out. The steeper it is, the more they are close to each other. At the very end, they become not very steep. Let me spin it up, see? Then the circle becomes pretty empty. Let's spin it down like so, pretty cool. So, and then there also might be a curve, right? That's a closed curve. Where is the function gets its maximum or minimum? On that curve, on that surface with these contour maps. And each contour maps tells you the gradient. So that's a pretty cool thing. And he modeled these and rotates its ellipses everywhere. So I like these levels, very impressive. And I think there was one more he sent me, which was here. This one. Yeah, he definitely coded some really impressive stuff. They do not exist anywhere in the internet yet, except his website. So I asked him to give me the link, the access, and he was very nice enough to share for free Marco. Marco is a very cool dude from Serbia. He's on my floor, so in the lecture building, so I talked to him quite a lot. So let's see. I think the best ones are here, and heat maps are really cool. So not only he wrote all of this, but he coded all of these gradient descent and ascent stuff, which, check this out, all move like so. So you can see this is how the plane can be described, tangent plane stuff. And then this is the best one, steepest ascent and descent. So gradient contour surfaces. What is the fastest way, I think here, to go down the mountain? That will be steepest descent. And that's where I showed you when you drop the ball, where the ball will gonna go. That's from the exam 2. Here. Heat maps. Oh yeah, these ones. So that is pretty cool. And it also explains really well contour maps and heat maps. Check this out. It's very important for people who are engineers and physicists to understand how differently you can describe the same thing. First of all, heat maps are created like so. In this case, the yellow one is the highest point, and the blue are the deepest points of the ocean, for example. And then there's a mountain above the ocean, right? Here's a side view. It's pretty cool. And then mathematicians like both heat maps, which are color-coded maps, and contour maps. You can see them over there. So this is how it looks from this point of view also. But this is the best one, is the contour maps. And the contour maps is the one we try to teach you how to recognize them and work with them. And I think, let's see. Can I walk on this? Yeah, and I can walk on this. That's why I wanted to explain that. Pen. What the heck is pen? Okay, never mind. So when I'm trying to walk, move it. Okay, never mind. See how it moves on the contour map. This is the hardest one for students, is to understand contour maps. When it's very steep, the contour maps are close to each other. When it becomes close to the flat parts, they're very far from each other. When there's no contour maps, there's no information to show. So why would you put a contour map there? Very interesting. Zoom. Where? Okay, doesn't matter. So that's why when on the exam, you will see no contour maps. On the graph, try to see flat surfaces because there's nothing to show there. It's not increasing and decreasing. So it's zero. The gradient here is zero. When you see contour maps far from each other, you will see that something is not changing too fast. And then when they get super close to each other, that means they're going down really fast or going up a lot. That is the idea of the descent or ascent. In this exam, we don't have ascent or descent anymore, or maximum, minimum, or saddle points, but we do have vector fields. So you know that they should be perpendicular to contour maps. So how to go down this mountain really fast? I'll point the arrows down, 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 perpendicular to color maps, to contour maps. Imagine you're standing at the edge over here. What is the fastest way to get down this mountain? Jump from the cliff. That's a bad joke, but it's exactly what's happening. If you drop the ball over here, it will roll down fast over here. And that is why the arrows will go perpendicular to the contour maps, because you're jumping away from the contour map. If you're walking towards the contour map, not perpendicular to it, that is not the fastest way to get down. You're just circling the mountain. Make sense? So that's gonna make sense. Same with hiking. If you're going up, then it will point towards the middle. But it's the fastest way to go up, not going around. That is why they're not following the contour map, the arrows. Little arrows will go perpendicular to them because they represent the fastest ascent and the fastest descent. And that's called gradient, ascent and descent. And that is the idea of the cross product of the R sub U and R sub V. They create normal vector, and normal vector, if you remember, is perpendicular because it's a result of the cross product. So all of this is connected. I want to show the big picture here. To the very first chapter of the vector definitions. Two vectors on the floor, the third vector perpendicular sticking out, that's a normal vector. Normal vector is connected to the steepest descent and ascent because also it's perpendicular to the tangent vector. Tangent vector tells you how things are moving and where. Normal vector tells you what is the fastest way to get out of that place. So to get out of this mountain, you go perpendicularly to the contour maps. And that's why normal vector makes sense. It's perpendicular to the tangent vector. And that's a connection between A and T and B vectors. If you remember that, we don't really care about the size of the normal vector. We care about the direction. Tell me, where is the fastest way to go down? Over there. So we don't care how far to go. That's why we unitize the normal vector. That takes us to the connection of those topics, the three vectors, T and B. Finally, to summarize all this crazy stuff is we learn how to find if there's a wind blowing around this mountain, which is very realistically, there's a wind here. And it's maybe strong at the top and then not strong at the bottom. Is it blowing into my face? It's blowing perpendicularly? Perpendicular is fine. If it's blowing perpendicular to me, it just takes me around the mountain. So I don't really change up and down direction. And that's why I don't care about that. But if it blows behind my back, it helps me to go down faster. If it blows towards my face, I'm going down slower. And that is the connection of the flux, which is the you and all other people with you going down the hill against the wind. That will be negative number of the flux, right? Because wind is against you. At some point, wind helps you, then it will be positive. You add up all of those winds together. If the final result is 0, then the total work of wind was 0. It was helping you and against you. But at some point in total, it was 0. If the total is positive, it was helping you to go down faster. And then if it's negative, it was hard for you to go down because wind was keep pushing you back. So total work done by the wind of one particle was a simple integral. Double integral, so that was line integral. Double integral, which correlates to surface integral, extends the line integral into upper dimension. Now you're walking not over the line, you're walking over the surface with the wind blowing down, going down the mountain with the graded descent, which has maximum and minimum. That's called flux. So either you imagine the blood going through your veins, it's a whole crowd of blood cells going through, that creates a flux, and how fast does it go? Very fast on this hand, but very slow in small vessels of the kidneys. Actually, it's a known thing that liver and kidneys have very small vessels, such tiny vessels that blood barely goes there. And that's why some of those parts have less oxygen than others, and they die first if you lose blood. So that's very interesting. The flux there is different than the flux in other places of the same organ. So somehow kidney and liver don't have the same vessels everywhere. So all of this is connected between each other. And then Green's theorem, I think actually it has here, it doesn't have, oh, too bad. They go to statistics and probability here in this class. But Green theorem goes to Stokes theorem in upper dimensions and explains how all this works in upper dimensions. And that's also very interesting. So you guys not done working with upper dimensions yet. You should know that there's so much more to that. So I think that is all gradient descent. And then coding, if some of you are computer scientists, you'll be coding that gradient descent algorithm. And it has several algorithms looking like this. The very next step should be always optimal. That's basically a very basic idea of explaining what is gradient descent is. It's more complicated than that, but in general, this is the picture. The very next step should be the fastest one. If you messed up at the beginning and you went to the wrong ladder, so there are many ladders to take you down from the building, of the roof of the building. If you took the wrong ladder from the very first step, then next step will have to follow that mistake. So that's very interesting that the very next computer only checks the very next step. And that's this representation of little arrows. If the ball goes to the right, then it will have to work with the descent on the right. If it goes to the left, and the left. The explanation behind this is you're hiking in the mountain, you did not calculate properly the time, you end up to be in darkness. Now you have to go down. You have only flashlight and you only see a little bit around you. That takes you to 2D. On every step in 2D, you're choosing the descent. Make the step, next circle, descent. And that's how it makes this code. N equals n plus 1. And every time you take gradient, which are partial derivatives, find the smallest one, and then make the step. And the next step repeats. And at some point, it should take you down the hill. It's to the some hill. It's actually interesting to understand it's some local minimum. You may be actually stuck at some wrong minimum, not the smallest global minimum. That's the global idea of this whole class, kind of. So in general, it's very interesting. You guys just should take it as 15 weeks. It's more interesting this way, because in 15 weeks, you actually enjoy it more. But high respect that you are surviving so fast, such a fast course. I would not do that. So we were discussing it between several mathematicians that none of us would choose this class as a short section. It's just crazy. So I said, my students are either genius or crazy, or they just very brave. So it's maybe a little bit of everything, because this is a very hard course and goes very fast. But I think without the cumulative final exam, it is doable. The third exam is doable. That's my optimistic ending. This is doable. Just like lots of formulas, parametrization is annoying, lots of graphs, but it is doable. So I'm actually definitely holding fingers for you, cross fingers that you can do it, because that's it. Just last exam, and it will be nice. People get good grades. So that will be fantastic. And then I plan to post grades really fast. I don't have a choice, actually. I have to post it really fast. And then people have to go to the B section. If I don't pass it fast, if I don't post it fast enough, people will lose a seat. This is the line integral. People will lose this seat in the B section, or lose the scholarship, and it will be my fault for delaying it. So I will have to post it really fast. This is really cool. Look at this, what line integral is. This is 2D, and then they show the mountains. What is your path from A to B if this is a mountain hike? See, that's one of the explanation of the fence. Why am I keep mentioning the fence? Because this is what it means. Line integral takes this hike, flattens it, and then calculates the areas, all areas below and all areas above using this formula, F times derivative of R, because it's dr, right? So let's see it again. Looks very nice. It's a heat map. It's flat. What is the path from A to B? Looks like a line. It's two-dimensional. But then when you make it three-dimensional, what if this line has height and up and down? That makes it a line. Moreover, line in 3D. That creates a fence. Let's make it flat and see how deep it goes and how high it goes. Find the lengths from A to B. Let's show it as an integral. We will have some negatives and positives. That's integral. So R prime multiplied by the function. That is a very good explanation of the line integral, one of the best ones actually. So I will post it here. Line integral. Very cool. What do you think about stuff? Kind of that's all. 14 people still here. Wow, people are still here. That's impressive. I just saw a couple of people. For me, it's enough not to talk to myself, but impressive that so many people stay. How do we get to you as a I actually differential equations is my specialization. My PhD was my research was in differential equations, but we have people hired specifically to teach differential equations, and they are tenure professors and stuff. So I don't usually get to teach it. I don't stay on the way of those fancy people. So I teach calculus 1, 2, and 3 is a nice sequence, and then let people go to the upper level. I was offered to teach discrete math at some point in linear algebra. So I might do it, we'll see. But we don't have schedule for spring yet, for fall. Pause. It's too early.